Hello, and welcome to our project on investment in climate services and early warning systems. To start off, let's introduce our team. We're a group of 5 undergraduate data analytics students from Utah State University. We have Chloe, Morgan, Brooke, Hannah, and me, Adelaide Berry. As the world shifts focus to building more resilient communities in the face of climate change, there has been a worldwide push towards funding adaptation-related projects. Through adaptation, we can minimize the negative consequences of climate change and build resilience to protect lives, infrastructure, and natural resources. With this push, increasing ease of access for investors is necessary. Major climate change funding sources such as the GCF, the World Bank, GEF, and AF have been making efforts to equalize the distribution of their projects between mitigation and adaptation. Still, there are many different sectors and components within adaptation projects. Given our problem statement, visualizing and understanding these different components in the context of millions of institutions and projects is overwhelming. But with strategic use of automated technology, we can simplify the process of determining where funding is needed for our stakeholders, the WMO and the USDA.
In order to obtain the necessary project information and financial components, we knew we needed to develop some kind of web scraping tool. Due to the scope and time constraints of this project, we chose to focus our efforts on developing a quality web scraper for just one of the websites given to us. After a manual analysis of all of the websites, we chose to develop a tool for the Adaptation Fund project website. We chose this website because it has a complex dynamic interface, which added an extra challenge to developing our tool and made a proof of concept that was more applicable to a variety of future applications. In our code, we implemented a combination of Selenium and Beautiful Soup, a web automation network, and a common Python library. This combination helped us efficiently scrape the dynamic pages and parse the HTML content, extracting vital information needed for our models such as project components, project titles, funding institutions, countries involved, and more. Then we cleaned the collected data and saved it into 2 separate CSV files.
Once we had our CSV with the web scraped project details, we needed to find the best method to map the 12 given early warning systems and climate services components with the projects in our database. Initially, we explored the possibility of using the TF-IDF technique, which is commonly employed for direct keyword mapping. However, we realized that this approach might not be suitable due to the subjective nature of the project descriptions. We needed a model that could capture the semantic meaning and relationships between the words. To accomplish this, we turned to the powerful BERT model developed by Google. BERT is a state-of-the-art transformer model renowned for its ability to encode text effectively. We accessed the BERT-based uncased model through the transformers library developed by Hugging Face. From there, we calculated the embeddings for both the project descriptions and the 12 components, and then used these values to find the cosine similarity values between the components and project descriptions. These scores were then normalized and employed as weights to calculate the financial flows associated with each component and project.
Using this resulting data, we've developed an interactive Tableau dashboard that offers a user-friendly interface to interact with and analyze our findings to create ease of access for our investors. First, we've created summary charts that illustrate the geographical spread and concentration of projects, allowing investors to see where they have been implemented across the world. On this map, the darker colors represent more projects in certain areas, which shows how few countries and regions are covered on the Adaptation Fund website. If this project was expanded to include more websites, it would illustrate a more accurate distribution. On the top, the component stores are normalized and utilized as weights. This allows users to see the component distributions and narrow these down per project or country, depending on the investor's interest. For example, if I was an investor interested in projects from India, I would click on the country or manually search. This will show overall what components projects in India focus on. We also took the component similarity scores and multiplied it by the grant amount, creating an estimate of dollar amount spent on each component. This allows investors to see which components are being funded more or less to provide them with direction. Another helpful filter we've added is that of max and min components. This allows us to see the component with the highest or lowest similarity score for each project. Based on our estimates, this would also be the component with the most resources or finances dedicated to it. For an investor interested in governance, finding those projects is now very simple. This analysis holds immense potential for investors making informed decisions regarding climate finance allocation to quantify their impact on climate services and early warning projects.
We are mentored by the Analytics Solutions Center in the Department of Data Analytics and Information Systems at Utah State University Huntsman School of Business. Our source code and project is published publicly and available now on GitHub. This journey enhanced our technical skills with exposure to data that matters. Our teamwork fostered a collaborative spirit while illuminating the path of climate sustainability through data-driven insights in our endeavor to aid the funding of a fearless future.